Okay, welcome back, everybody. Oh, let me let in a couple more people here. Okay, all right, this is the beginning of the third week. So this semester is going pretty quick. Anyway, quick question. Any questions concerning today's exam? Don't forget we have an exam today over chapters 1 through 3. It's a short one, maybe I believe 24 questions. All right, I got a couple fill-in types, most of them multiple, all the rest of them multiple choice. So nothing complicated, keep it simple. We're not trying to complicate things, okay? Don't overthink it. 9 times out of 10, the first answer you think of is more likely the answer. All right. Yes, there is, Amy has a question. Yes, there is a calculator you can use in the lockdown browser. You may need it, okay. On the browser itself, I set it up so there's a scientific calculator you can utilize. Some people like it, some do not. See how that works for you. Hopefully you have a calculator you can use, one you can hold in your hand. Last resort, if you have to use the computer calculator, last resort, pull it up and then make note of that, send me an email that you had to use the computer calculator, but you shouldn't have to. The one that's given to you there on the lockdown browser should work for you. Okay. Any other questions? Give yourself plenty of time. I believe that's time for 75 minutes. So more than enough time. On average, it takes, people are taking from 50 to 60 minutes. Okay. So any other questions? Any questions concerning the material we covered 1 through 3? Okay. All right. The question is, if we use measurements, do we use only a metric system? Yes, unless the question says to convert from one unit to the other, from English to metric. But with respect to anything other than conversion factors or converting from one unit to the other, we always use the metric system. That is correct. So you'll see kilogram, grams, so forth. Milliliters, liters, meters, millimeters, things like that. Okay. I think the calculations you're going to run into down the road basically will be in the grams, because we're going to be converting from, let's say you got an X amount of grams of A as a reactant. How many grams of A product do we make? Okay. And so this chapter on conversions is an exercise to help you utilize that ratio system, that ratio system, and I forget the multiple names for it, but basically keep track of your units. That will help you out, because when we get into the calculations of chemical reactions, keeping tracks of units would help out. There was a question and I put it only in, okay. Well, if there is, as any good point here, as with any of the assignments, if you ever have a question that you know it is correct, or maybe you think it's correct, shoot me an email, tell me where it's at, what number it is, and I will definitely look at it. Okay. Again, Canvas is definitely not AI technology. It's, you basically have to tell it everything. So if you inadvertently add an extra decimal or a space or something, it will count it as wrong. Okay, so just for all of you, anytime you have an answer that's you know it's correct, or your question, shoot an email. I definitely will look at it and definitely give you credit for it. Okay. Now spelling is crucial. Most of the time, this is spelling error. I give you the first one. That's a freebie. Okay, but after that, it's you know, science is very exact, and so be very careful when you type things in to make sure that you type it in correctly. Okay. All right. All right. Exactness is very crucial. I've had many. Well, I give you a classic example of this. Many years ago, NASA. You know, you think NASA, you get all the brains there. Well, NASA had a problem when one of their missions. I forget exactly what it was, but there was basically two groups of teams working. One of them, for whatever reason, was utilizing the English unit, and the others were using the metric unit. And somewhere along the line, they combined it and didn't work out too well. Okay, big problem. So exactness is very, really crucial. I also, from a personal perspective in the medical area, I've had situations where people were going to inject an X amount of material, which was not correct. All right, so always double check your work. I always, do you double check our, yes, I always look in there and look for things that I'm always trying to correct canvas. So yes, yes, I do that. And occasionally I miss one. So if I miss one, feel free to shoot me an email. Say, hey, you know, lab, whatever, question number, whatever. I'll be more than happy to look at it. And if it's an overall thing, I will correct everybody. Okay. So you may see occasionally an alert from Canvas saying something's been regraded or you've been given credit for a question. All right. Any other questions? Good questions. Yeah. All right. Well, I tell you what, no more questions then. I will continue with chapter 5. Okay. Chapter 5. Let me make sure here. Hold on 1 second. Okay, chapter 5. Now, we introduce the we're going to error report. Something happened here. All right. Now, we're going to talk, this particular chapter deals with the atomic structure. Now, we've introduced the elements, okay? We introduce the particles that these elements are made up of, the proton, the neutron, and the electrons. Those are the components that we're going to focus on, okay? And we introduce what the model was at this point, meaning that there is a nucleus, where the proton and the neutron exist, and then the electron is somewhere around the element. How it was, we didn't quite understand until we got obviously more information. So the model that I'm presenting now, tomorrow this thing can change completely, you know, but at the current time, this is the best model we have with the data that we have, and so forth. And so it may like totally change tomorrow, next week, whenever. Okay, so what we're going to talk about is the atomic structure. Now recall, we talked about the proton and the nucleus, where they had a fairly large mass, and we assigned it a relative mass, a AMU, atomic mass unit of 1. So the proton had a 1 unit AMU, and the neutron had a 1. Okay. Now, the electron relative to the mass of the proton and neutrons was extremely small. So we essentially gave it a 0 atomic mass unit because it's so tiny relative to the other components. And yet, as tiny as it is, it has a drastic effect on chemical properties. It's the electrons where all the action's happening. That's where everything is occurring with respect to bond formation, all kinds, with respect to physical properties, okay? Anyway, we're going to talk about the atomic structure. But to do that, the fact that the electron is so small that it behaves like a light property, like light does, okay? Because being so small. Keep it in mind, we gave it a 0 atomic mass unit, but it still has mass, but it's so tiny that it behaves as a wave of light. So we're going to briefly discuss about light itself, okay? Our model for lights is that it exists as waves, okay? So electrons being so small can also exhibit wave properties. Now, how do we describe a wave of light or a wave of electron? Well, we use this model here, okay? Now, what we have is following. This blue light here represents a wavelength. Now, if we take a point, let me change the color here. Anywhere in this wavelength light, in this case, we're going to pick a point right here. And notice we got a little hill, and then we got a little trough here, okay? And then we got another hill. Well, the next hill at this point right here represents the other wavelength, a new wavelength, okay? So every wavelength, the distance of a wavelength is the distance between these 2 points. And we call that, we give it a symbol. That symbol is the lambda, which is the wavelength of light. And it could be, the wavelength can vary with respect to distance. It's the measurement that we actually have. It could be, from, I'll give you an idea. I'll give you an example. The radio waves, if you're listening to the radio in your car, those are humongous, very meters. They're in meters with respect to the wavelength. They're very big, okay? If you ever had an X-ray done, that's electromagnetic radiation. The term electromagnetic radiation represents all the light that's out there. On one end of the spectrum, we have radio waves, where they're very big in length, the wavelength. And then the other end of the spectrum, we have things like gamma rays. And in that spectrum is, say, X-rays. You're all familiar with X-rays. Those X-rays are very, very tiny. Now, what do we know just from what you know about the energy? We know that the wavelengths are pretty not so much energy in them, okay? They were easily blocked by buildings, you know. They're easily deflected, and a lot of times, you know, you don't get good radio frequency. You can't get a good station because it depends on the area that you're in. The wavelength gets blocked. Whereas X-rays can be very powerful. They go right through your body. They're so tiny, they go right through your body. And it's a good thing in the sense because we can use that to make images and take a look at what's underneath our skin, okay? Now, yes, they will be blocked by, you know, things like lead. A thick sheet of lead will block it. But then we got gamma rays that even have more energy, and they go right through that, no problem. Okay, so on one end of the spectrum, high energy, very deadly, and the other end of the spectrum, big wavelength, not so deadly, okay? All right, so we have this called the wavelength, and that wavelength varies from wavelength to wavelength. It depends on the electromagnetic radiation, okay? So as I stated, we have the wavelength denoted by lambda, okay? And then we have the frequency. Now you're also familiar with the term frequency, or maybe you're not. But if you have a computer, which you're working on, you probably looked at the specs and said, oh, look, I found out I got a computer here that's operating at a certain frequency, maybe 2 gigahertz or 3 gigahertz or whatever. Your cell phone, if you're using that, its processor is working at a certain speed. That frequency is represented by this symbol, looks like a V, it's called mu. And what that represents in this case is how many wavelengths in a given time unit, okay? And so let's say, for example, from this point to this point, and generally the time is 1 second. So the question is, how many wavelengths? So we got 1, 2, and 3 wavelengths occur within that distance of time, if you will, that time or 1 second. And so that is called the frequency. That represents how many cycles occur within a given time unit, which is normally 1 second. And so in your computer, if you're operating at 2 gigahertz, that thing is operating, there's 2 billion things occurring within 1 second, okay? Pretty fast, fairly fast. Not as fast as your brain operating, but it's still pretty fast. And considering that my first computer I purchased in 1982, and it was operated in megahertz, kilohertz, K. It's extremely, now we're up to gigahertz. So quite a jump in that time span. So wavelength is the distance between waves, okay? And frequency is the number of cycles that occur within a second. So obviously the more things, the more cycles that occur within a second, the higher the frequency, okay? All right. So let's take a look at this here. And if you look at 2 graphs, excuse me, so I woke up this morning and there's sneezy nose. All right, so if we look at the top graph right here, this represents a low energy light, okay, relative to a high energy light. Now, with respect to wavelengths, you can see that the low energy has a wavelength from hill to hill. Now, it doesn't have to be from hill to hill. You can go from trough to trough or any point of the first. I could pick a point right here, but if I pick the second point, it's going to be in the same spot. So that distance, be it on top of the hill or the bottom of the hill, makes no difference. That represents the wavelength, okay? That is lambda wavelength. You know, if you look at the diagram on the bottom, the distance between the 2 hills or the 2 troughs is relative to the one on top is fairly short. So we got a long wavelength depicted on the top of this diagram and a short wavelength depicted in the bottom, okay? Now, within a given time unit of 1 second, and, you know, we could pick this distance from here to here as the frequency of 1 second, and you can see that in that time span, there's 1 wavelength that goes through, 2 wavelengths, whereas down here we got 1, 2, 3, and 4. So the bottom one obviously has a high frequency, where the top one has a low frequency with respect to each other. We're comparing the wavelengths with respect to each other, okay? And so what this means is this: if I have low energy light, I will have a long wavelength. So that could be the radio waves, for example, and a low frequency, okay? Because they're so big. If I have a high energy light, I'm going to have a short wavelength, and it's going to have a high frequency. So that could be represented by, say, X-rays, okay, where they have high energy. All right. Now, we can see here that by looking at the 2 different wavelengths, that B has the higher energy, whereas wave A is of lower frequency, okay? Now we have the spectrum, and then we call it the electromagnetic spectrum. Some people hear that term electromagnetic spectrum and they think X-rays. Well, that's just part of it. Okay, electromagnetic radiation is basically light, if you will, in different wavelengths. On the far right is the radio waves. Okay, very long wavelengths, up to meters. Okay, and the far left we have gamma rays, very, very short wavelengths, and very powerful. Now, this scale here is not, this spectrum here is not the scale, but the visible, what we see is very small relative to the whole spectrum. And that represents, that there represents the visible spectrum that we are able to pick up on. Those are the cells in our eyes called cones that pick up specific wavelengths, but only in the visible. Ultraviolet, we're all familiar with ultraviolet. Okay, you sit in the sun too long, what's going to happen? You're going to get, sunburn. Well, that's attributed to the ultraviolet lights, which can be very, very deadly. It could be very bad because it could cause all kinds of genetic problems with the skin. If there's too much UV light, it will definitely affect the plants out there. And given that our ozone layer is depleting, or has been depleting for years, normally the UV light is deflected, interacts with the ozone. And since we've got a hole up there, we're getting more UV light coming down. All right, it is higher, ultraviolet is much higher in energy than the visible. And then below the visible, we got the infrared, which obviously we can't see, but we do have instrumentation that will allow us to view that. And then down here, next time you make up some popcorn, you get the microwave, okay? The microwave. Now, the microwave is much less energy than the visible. Anyway, anybody by chance, the next time you use your microwave, anybody have an idea as to how that microwave works? Why is it cooking your food? Anybody have any? It's kind of related to what we're going to talk about. Okay. Now you're gonna heat your food up, or you're gonna make some popcorn. You get it, you stuff it in the microwave, hit a button, come back, 30 seconds later, a minute later, your food is warmed up. What's going on there? Anybody ever thought about it? Induction? Not quite though. Just a good answer, but not quite. Okay. Now, all this electromagnetic spectrum, okay, is energy. Some of it is low energy, some of it is very high energy, okay? So what happens is when microwaves are subjected to your food, water will absorb that energy. In fact, if you got right now, remember that screen that we're showing with J.J. Thomson and so forth, and that fluorescent screen? I said, while those particles hit that screen, transfer that energy of the particles onto the material of the screen, they absorb it. Now, nature being nature, doesn't like to be into the excited state, because whenever matter absorbs energy, it kicks it up into what we call an excited state, a very specific excited state. It won't hang out there very long. It's going to drop it back. It's going to go back to the ground state, the most stable state. And in doing that, the conservation of energy law tells us that whatever energy goes into a system, it's going to release it. Same amount. It will release it either as light or reduce it as a heat. Okay, but all that cumulative will be the same amount of energy it absorbed. And when that fluorescent light gets rid of the energy, it releases it as light. Okay, and what's happening here with respect to your popcorn is the water molecules will absorb the energy of the microwave. Okay, it excites the water molecules into an excited state. Water molecules are hanging out here in the ground state, minding their own business. They get kicked up to an excited state, a very specific amount though, okay? Because all the energy here Every wavelength is associated with it in an X amount of energy, like I stated. So that water molecule absorbs that energy. It excites the water molecule in your popcorn, okay? The molecules start vibrating, relative to each other, relative to themselves, okay? They're in the excited state. It's not going to hang out there very long. And so it's going to release the energy back away from it and get back into the ground state. And when it does release the energy, guess what? It releases it as heat. And so the food around then absorbs that heat and your food gets warm, okay? So it's a matter about energy. We're going to learn that these electrons do the same thing, in that these molecules get excited, these electrons get excited from their stable state to the next state, okay? To the next state. And then we'll release that energy once they go back to the ground state and release it at a very specific amount of energy, okay? So it's all about energy here. All right, so 1900, remember our models, we talked about other scientists in this time period. Niels Bohr, J.J. Thomson and so forth, but here's another guy, Max Planck, another scientist, very famous. In Europe, there is a Max Planck Institute. Now, all these scientists living during this time period, a lot of stuff was happening here, a lot of stuff. Just like a whole plethora of information in our model about how matter was put together came about. Well, Max Planck proposed at that time, it was controversial, that energy was emitted in small bundles, okay, which he called quanta, okay? And that energy is not a continuous emitted phenomena, that it is a specific energy, okay? And if it's of a specific energy, guess what? It is a specific wavelength, okay? Now, he called these units of light energy as photon. Hence, here we got photon torpedoes, right? Think about that. Light has a lot of energy. You don't believe me? Think about lasers. You got lasers out there that cut right through metal. A lot of energy there, okay? Still don't believe me? Go sit out in the sun for about an hour with no suntan. Tell me what's going to happen when you come back in. That energy that you picked up from the sun, that ultraviolet light, causes a lot of problems to your skin. All right, so these, we use a term called quantized, and that light exists in levels and is not continuous, okay? Now, how does that relate to electrons? Well, we'll get there, okay? So this is what he meant by continuous. Unlike this wedge here on the left, where he got the balls rolling down the edge, where that represents continuous energy. What has been proposed is that energy is like these steps on the right, that you start off at the bottom. That is, there's a question here. Yes, Planck's constant. Edwards Eduardo had a question about Planck's constant, and that is exactly him. And so here, what is proposed, that we start off on the ground state, right here in the ground, as we call that the ground state. Okay, the unexcited state. Okay, and then when we go up a level, say the first step, we have a specific amount of energy. That step represents a specific height. And as we continue to go to different heights, every height is very specific, every step, of specific energy. And it's not continuous like it's shown over here. That was the controversial idea that came about. Okay. So anyway, with Planck's work, here comes, Bohr, Niels Bohr, another scientist, obviously. He proposed that electrons obviously orbit around the nucleus, but furthermore, we had that idea that that's where they're at. They got to be there someplace, right? but he proposed that they exist in very specific energy levels, very specific energy levels. Specifically, if you look at your periodic table, and you can see now, I can bring this forward. Notice what I did to my periodic table. On the far left, I put the numbers 1, 2, 3, 4, 5, 6, and 7, okay? These represent, well, we're gonna learn that these are periods, okay? And these elements all exist in the same period. So element from potassium all the way across to krypton, they exist, it exists, all those elements in between exist in period number 4. Every number there represents a specific energy level. So we got the first energy level, the first one, where hydrogen and helium exist, and they got one energy level. Those electrons that belong to hydrogen and helium, they're going to sit in the first energy level. When we move up to lithium, right here, guess what? We have to introduce a second energy level. Not only does lithium have the first energy level, it has a second energy level. And its outermost electron, it had a lithium, we know it's number 3. It has 3 protons and 3 electrons. 2 of those electrons exist in the first energy level, and 1 electron exists in an energy level number 2 on the outside, okay? And the same goes with that all the way across to neon, okay? So those numbers, let me clear up my mess, I got a little messy there. Those numbers represent specific energy levels, right? We only have 7 of them. When we find element number 119, we will probably have energy level number 8. And it will be right underneath number 87, whatever element that becomes, if we find it, okay? Okay, so. Back. And this is one reason I referred to the periodic table a lot. It's going to tell us, it gives us a ton of information, but more importantly, it's going to give us how these electrons are occupied, how they occupy themselves for that particular element. And the textbook uses this formula that you can use, you may have to memorize to figure out where these electrons are. But knowing their position on the periodic table, you can get to that information much more rapid, I think. Anyway, the electrons orbit around the nucleus, kind of like planets, okay? But more in the 3D, similar like our solar system, but not exactly, because we live here, obviously, well, all around us, we have in the 3-dimensional world. So these electrons are, if you will, around 3-dimensional. You got to think X, Y, and Z. All right. Now, these orbits that I just described in the periodic table, there's 7 of them. They're called energy levels or shells. Okay. I prefer the term energy level because that's what they are. All right. I think of shells, I think of oysters for some reason. So I don't know. If shells work for you, then go for it. Don't let me stop you. That's how you want to call them, that's fine. But you've got 7 energy levels. We are going to find out here that within these 7 energy levels, there are sub-energy levels that we're going to call orbits, okay? Orbits. Okay, so every orbit or energy level has a specific radius and a specific energy. So there are certain distance from the nucleus. Now, right now we're talking about electrons, and F side note here that right now we know the protons are in the nucleus, but we didn't know much about how they're there, how they adjust themselves, the protons and neutrons. We're learning, at least the new models are coming out, that even the protons themselves are in specific energy levels down in the nucleus, but we're not going to talk about that. I'm just throwing that in there. Okay. All right, so how do we represent these orbits? Is denoted by this diagram. We have the nucleus there, and then denoted by, there's 3 energy levels here denoted by the dotted lines, the dotted circles. But keep in mind, think 3-dimensionally. Right now, this is shown in 2-dimensional. So we've got energy level 1, energy level 2, energy level 3, 4, 5, 6, and 7, okay? And within each energy level, that's where the electrons exist, okay? Now, how do we know this? Are we just, making something up? Well, sometimes we do. When we have a theory about things, how things work, we have a hypothesis about how things are made. But this time we don't. We really have actual data to demonstrate that electrons are shown or exist in specific wavelengths, and that is shown by what's called a line spectrum. Let's kind of change gears for a little bit, okay? So it says, why did Bohr think that the electrons orbit in quantized energy levels, okay? It is because he found out that the behavior of gas is sealed in the gas discharge tube, which is no more than a fluorescent light bulb. That's all that is. You take a gas, seal it in a tube, you got electrodes in there where you're gonna run electricity through it. You're putting energy into the system. What happens? The molecules of gas in the tube get excited, right? They get excited, and then they go up to the next excited level where they're not going to hang out there very long. They drop back down to the ground state, and in doing that, they emit the energy that they absorb, and they emit it as light. That's how it fluoresces. That's how most anything really works. Even an incandescent light works. The molecules of the wire get excited, just like if you got an electric burner in your stove, the molecules on that metal get excited, okay? And then they release that energy as heat. Well, in fluorescent bulbs, if we were to slow time down and watch a fluorescent bulb, that thing would flicker on and off because the molecules are going from excited, ground state, emit light. Excited, ground state, emit light. Okay, and that's what's happening. But it happens so fast that to our eyes, we perceive it as continuous. Okay. All right. So if we were in the lab, we can actually demonstrate this, but unfortunately, we're not there. So what we have here, I got to demonstrate it using these slides. When we take a tube of gas excited with light, we end up with what is called an emission line spectrum. We take the light that is emitted and we run it through a prism. A prism is nothing more than a glass that separates the energy into their different wavelengths, okay? Denoted like this. Next time you see a rainbow out there, if we ever have rain, you see a rainbow, okay? The water droplets are taking the light and diffracting it and breaking it up into the different wavelengths, and that's why you see that. You see those wavelengths that we can pick up with our eyes. So if we take this tube there's a glass tube with some kind of gas in there, hit it with some electricity, lights it up like a fluorescent light bulb. We take its light and we run it through a slit, and all that's doing is just focusing the light, okay? Nothing fancy. Just focus the light and focus it into a prism. The prism then breaks it up into the different wavelengths, and it takes this white light, if you will, and it breaks it up into the different wavelengths. And we end up, with different wavelengths with specific values that are measurable. So these units here, nm, those are called nanometers. Nanometers, 10 to the -9. Okay, you've heard of nanobots and nano, we're down to the atomic scale, very, very small. And notice here, we have 1, 2, 3, 4 lights, wavelengths that we are able to separate. Now, the neat thing about this is hydrogen. okay? This is the fingerprint for hydrogen, the fingerprint for hydrogen, okay? No other element would have that particular fingerprint. And this is one way that scientists use to analyze light coming from space or from anywhere and be able to analyze and see what that material is made of. Obviously the light we get is very complicated, so you got software that can separate and do all kinds of stuff, break it down, and then tell you what's in there, okay? So this hydrogen is very specific, has a very specific light emission spectrum, okay? Now, if we do that to a variety of different elements, things like lithium, sodium, potassium, so on and so forth, each one has their own emission line spectrum, its own unique colors. And what these lines represent are these electrons that are going from the ground state and being excited to the next state, the excited state of specific energy amount. And then they're not, like I stated, they don't hang out there very long. They drop back down to the ground state. And when they do that, they have to emit that energy they absorbed, and they emit it as light, okay? A specific energy. And so this here depicts what I'm talking about here. This, we have the red is an electron. Let me change the color here. We got the nucleus here, and we've got some electron in some orbit, okay? We put energy into the system, either we heat it up or we hit it with some electricity. What's happening here, that electron that exists in whatever energy level it's at is kicked up to the next energy level, which is the excited state, okay? But that's not a stable state. This is the stable state right there. And when it's kicked up to the excited state, it's not going to hang out at that state very long, okay? So it's going to drop back down to the ground state. And when it does that, that distance represents a specific amount of energy that it will emit, either as light or heat. And that's what happens to the water molecules in your popcorn. They get excited by the electromagnetic radiation, okay? And then they emit that energy as heat. Now, the same thing happens, similar thing happens, if you ever think about it, is if you ever had an NMR. I want you to think about this. An NMR, very similar, is what happens if you're in the NMR, you're in this little, if you're claustrophobic, it could be pretty bad. But you go in this tube. Well, around this tube is a very powerful magnet. Okay, that's why you got to take all this stuff off, any metal and like that. Very powerful magnet. And when you run through that tube, the hydrogen atoms in your body, there's an electron, one of the hydrogen's first element's got one electron. It's rotating, and depending on this position, associated, if you recall from J.J. Thomson's experiment of the electron, that he put a magnet and deflected that beam. When that electron is moving, it has with it associated and magnetic component. So when you go through that tube in the NMR, okay, all your hydrogen atoms get lined up, okay? So you're being set up there, you get it all, you're getting magnetized. Well, you're not truly getting magnetized, but your hydrogen atoms are all getting set up to go one direction. Then you're subjected to electromagnetic radiation, not X-rays. You're subjected to radio frequency. So, so the radio frequency comes in, okay, which is energy, low energy, but energy nevertheless. The atoms are, depending on their environment, the hydrogen atoms are all lined up. They absorb that radio frequency energy, and depending on where they're at in their environment, they will absorb a certain amount of it and they will flip. Well, when that flip occurs, remember, it's an electron, causes a little current, and then that little current is picked up and eventually gets converted to a signal. This is beyond the scope of this class. But it happens because you absorb energy-wise the radio frequency. Okay, so, and then eventually that hydrogen atom goes back to the ground state. Anyway, excuse me. So what we know so far at this point, at least our model, okay, and I emphasize this is our model, which can change tomorrow. Anyway, there are 7 energy levels, okay, denoted by the periodic table 1 through 7. Okay, now within these 7 energy levels, there are sublevels. Okay, there are sublevels that we're going to call them orbits, and this is where the electrons exist. Now let me add one more step to this. All of this is purely mathematical. Initially, it was all mathematical. The models, the way the orbits are shaped, they end up being mathematical equations that we plot data, and when we plot the 3-dimensional data, we get a particular shape. And this is what our thought is what an S orbit looks like, what a P orbit, and the D and the F orbits. Okay. All right. So in the first energy level, there's only one orbit or sublevel, and that is the S. And we denote it by the coefficient 1. 1 tells you that it is the first energy level, and the S tells you what type of orbit it is. Okay. Now, if you look at the periodic table, you will see that the first energy level is right here. And the only two elements that have to deal with that, the 1s is hydrogen, and then we go across the table in helium. Okay? Hydrogen and helium. All right. Now, when we go to the second energy level, we continue with the S orbit, but then we introduce a new orbit, which we call the P. So the P's start off over here with boron. So we call it P superscript 1, P1, P2, P3, P4, P5, and guess what? P6. Over here we got S1 for the first group and S2. The superscript represents how many electrons are there, okay, for that orbit. So S superscript 1 tells you there's 1 electron. S superscript 2 means there's 2 electrons in that orbit. The coefficient tells you what energy level you're at, 1, 2, 3 through 7, okay? I realize it could be a little confusing right now. We'll try to put it all together for you here in a bit. So the second energy level, which begins with lithium on the periodic table, you got your table in front of you, you can see, follow along. You start with lithium and you move across, okay? And then you go all the way across to the next group, the 6th column, P1, P2. But anyway, the 2 represents the second energy level. Notice that first energy level has an S orbit, so does the second energy level. But the second energy level, we introduce now the P orbits. Okay, so the second energy level has 2 orbits, the S and the P. First energy level only has the S. When we go to the third energy level, we introduce a third orbit, which we call the D as in David. Now notice the trend here that everybody from energy level 1 all the way to 7 will have the S orbit, okay? All the way down. Everybody has an S orbit, okay? Starting with number 2, energy level 2, we introduced a P, and that 2 would have the 7p all the way down. Excuse me. All right, so when we go to the 4th energy level, we introduce the 4th orbit, type of orbit, and that is called the F as in Fred, okay? But it doesn't come into play until we reach the 4th energy level. The same is true for the D. It doesn't come into the story, it doesn't come into it until we reach the 3rd energy level, okay? And it doesn't really play a factor until we reach a specific element. All right, okay. So remember, the coefficient represents the energy level 1 through 7. The letter represents the type of orbit. We have the S orbit, the P, the D, and the F. Okay, the P, in the 1st energy level, there is no P. P doesn't come into play until we reach the 2nd energy level. Okay, same is true for D. D doesn't come into play until we reach the 3rd energy level. Okay, and the F doesn't come into play until we hit the 4th energy level. Okay, now let me go back to the periodic table. When you look at your periodic table and you look at your columns, the first 2 columns over here on the far left, denoted by 1A and 2A, this is right here. Notice there are 2 columns, okay? If we think about these as the S elements, and I have another periodic table here that I'm going to help you out with. If we look at these right here, that I've put a box in here, we're going to think of those as the P elements, okay? Notice the S elements, there's only 2 columns. We're going to have S1, superscript 1, and S superscript 2. In the P, we have 6 columns. Count the columns in what we call the P elements. There's 6 columns. So it's P superscript 1 through P superscript 6. Now, starting right here, the inner elements, if you count those, guess what? You're going to count 10 columns, 1, 2, 3, all the way to 10, to zinc is 10 columns. Think of these guys as the D as in David elements. So we have D1 superscript all the way across to D10, okay? And then finally, the ones that we pull out here, there are 14 columns here. Count them out, there's 14, okay? Think of these guys as the F, as in Frank, Fred elements, okay? And this is what I mean about when we're going to work about getting the electron configuration for every element. We can memorize this long equation, or we can just find it on the periodic table, determine what period it's in, determine which type of element it is, and almost immediately we can write out the electron configuration for it, okay? Using the periodic table. Or you can just use the long equation, you do that system. We'll do some examples. No worries, we'll do some examples here. All right. So again, I reemphasize, 7 energy levels, 4 orbits, S, P, D, and F. The P doesn't come into play until the 2nd energy level. The D doesn't come into play until the 3rd energy level, and the F doesn't come into the story, if you will, until the 4th energy level. And at this point, that's really all we need, these, because we don't have any more elements. When we get more elements, then we're going to expand on the orbits. So this here kind of diagram depicts what we just talked about. We get the 4 energy levels, okay? I'm not going to show all 7, but at least up to the 4. And then you can see that every energy level, that's where a specific orbit comes into play. Now, all 7 orbits have the, all 7 energy levels have the S orbit, okay? Only 6 orbits, energy levels, have the P orbits, okay? And only 4 have the D orbits, and so forth. See how that works? Okay, so when I talk about these orbits, what we're talking about is about regions in space where we discuss or we talk about the probability of finding an electron. Okay. Now, here's my drawback. I'm throwing my 2 cents in. Is on one hand, science is very specific in that we talk about specific energy levels. Okay. But then we throw in this probability thing, which is, you're shooting the dice, if you will. Einstein had a problem with this model because of this probability. He felt that no, nature's a lot more specific. However, at this present time, this is the best model we have, okay, until such time that it will change. And new things are being observed and so forth. And the model is getting refined. It has refined quite a bit. So we'll eventually get there. So what we have is this. We talked about the suborbits. Now, there is a maximum number of electrons that every orbit can handle. For example, the S orbit, okay, and I don't know, I was once asked the question why they use letters. It's a good question. I think we'll learn here in the shape the S, because we're going to learn that the shape of the S is round like a ball sphere, so that makes sense. The P, I don't know why that letter, or the D, and or the F. I suspect they're just following the alphabet. After that, you might get the G orbits. Who knows? Anyway, the S orbits, the maximum number of electrons that any S orbit can handle are 2 electrons. So we have 1s through 7s. The maximum number you can put in that orbit is 2 electrons. Hence, if you look back at the periodic table, the group 1 and group 2a, first 2, I said, think of those as the S electrons. Well, in the first column, I can put 1 electron, hence S superscript 1. And then when I go to the next element in the next column of group 2, I got an extra electron, right? I gained an electron. Well, that electron will go into the S orbit, and it'll be S superscript 2 for that electron. And then when I shoot across the periodic table, especially I'm still working on group 3, I jump into what I said, think of them as the P orbits. And I said there's 6 columns. Well, the P elements, I should say. There are 6 columns in the periodic table, starting with boron, go all the way across. 6 columns, and we got P1, P2, P3, superscript, to P6, okay? Because in the P orbit, first of all, the S orbit, there's only 1 S orbit, but the P orbit, there's 3 of them. And each orbit, wherever it is, the D, F, P, and S can only handle 1 electron, or 1, let me restate that. Every orbit, regardless of the letter, can only handle a maximum of 2 electrons. Since the P has 3 orbits, each one can handle 2, the maximum electrons the P orbits can handle would be 6, right? 3 times 2. In the D orbits, there's 5 of them. There's 5 separate D orbits. Again, each one can handle 2 electrons, which gives you a total of 10 electrons for the D orbits. And notice in the innermost, I said, think of those as the D orbits. I said D1, there's 10 columns in the periodic table of the innermost elements, 10 columns. And then finally the F ones, those are the 2 rows that pop out of the periodic table. There are 14 orbits, 14 columns, right? While in the F, there are 7 orbits. Each one can handle 2. Therefore, there's a maximum of 14 electrons for the F orbitals, okay? That's the maximum numbers of electrons it can handle. If you end up with 15, one more electron, what do? You got to go to the next orbit. Okay, so this diagram, which really I need to redesign. If you can imagine in your head, take this picture and flip it upside down, okay? Because you're really starting at the bottom, and this is the top level 1. So you can see in the level 1, that box represents the orbit, okay? And hydrogen, I'm going to put an arrow here. Let's make it different color so we can see it. That arrow represents an electron. So there's hydrogen, the very first element. Very first, it's in period number 1, okay? Period number 1, the only orbits are the s orbit. So if I needed to write the electron configuration, what we call the electron configuration for hydrogen, I would say 1, because it's first one, that's it, first period. And then S, now hydrogen is in that first column, okay, which is what we call, I said, think of those as the S elements. And it's only got one electron, so I write S with a superscript. That superscript represents that one electron. So that would be the electron configuration for hydrogen, okay? All right. Now, if this was helium, helium only has 2 electrons. So I will put another electron in there, another arrow to represent helium. So that would be the electron configuration for helium, He 1s2. Okay. Now I put the arrow in opposite direction, because what that means is when we have 2 electrons in one orbit, one of the rules of the physicists states that they can't operate in the same direction. They're going to be in opposite direction. So for right now, I'm just showing you 2 electrons. Now, once that's helium. So element number 3, who is that? Think about it. Look at your periodic table. That's lithium. Lithium has, lithium has, and I'm going to start doing this. Let me clear this up. Once I filled up 2 electrons, obviously that is the 1s2. That's a full 4 electrons for that first orbit. Now here comes lithium. Lithium's in the second energy level. It has 3 electrons. Look at your periodic table, right? Well, being the second energy level, I know it is 2s, and then 1. It has 2 of those electrons for lithium are in the innermost shell, because when we fill these up from the bottom, from the lower energy level, we fill them up as we go across, as we add more electrons. So the first energy level is full, 2 electrons go there, and the next energy level, okay, is the second energy level. That's where the third energy. So lithium, has 3 electrons. 2 of them are in the 1s2 orbit, and the one all by itself is in the 2s1 orbit. Now look at this. This is why lithium is in the first column, because what they share, everybody in that first column share this property. Their outermost electron, they all of them, everybody in column 1, group 1A in the periodic table, all of them have 1 electron in the outermost shell. Lithium has 1 electron in the second energy level, okay, outermost shell. If you look at sodium, which is right below it, it also has 1 electron, but it happens to be in the 3s1 level. And that is why everybody is in that column. We call that the valence electron, the outermost shell, okay? That's where all the action happens in chemistry. the outermost shell. Nothing's going to happen with the innermost shell. Electrons only in the outermost shell. And because what they all share in that property, one electron in the outermost shell, they all have very similar reactivity. That's why they're in that one column. Now, with that information, what do you think? Go move over to group number 2. What is it that everybody in group number 2 would have in common? Anybody want to extrapolate on what I just told you about everybody in group 1? What would everybody in group 2 have in common? We got it. Exactly. Trevor, you hit it right. Everybody in group 2 will have 2 electrons in their outermost shell. Yes, they're going to have different numbers. Okay. Beryllium has 4. Magnesium, its number is 12. That's 12 total electrons. But of magnesium's 12 electrons, 2 of them will be in the outermost shell. Okay. And that's why everybody in that group 2 will exhibit very similar reactivity. Now, the next trend, we jump over to where boron begins. It's the 3A group, okay? And that boron, with this information I just gave you, can anybody tell me what boron is element number 5. Can anybody tell me how many valence electrons does boron have? Okay, prime boron is number 5. 3, exactly, Trevor and Sam. They have 3. They belong in group 3A. Okay, how about fluorine? How many valence electrons does fluorine have? Find fluorine. Okay, fluorine's number 9. Exactly, 5. It's in group, hold on. 7. Yeah, I jumped ahead. I looked. Look at the group it's in. In Roman numeral, right above there is group VII. Roman numeral VII. That's 7. That tells you there's 7. Of those 7 valence electrons, 2 of them are in the s orbit, and guess what? Those other 5 are in the p orbit for period number 3. We'll get some more examples here in a bit. We'll put it all together. So I'm trying to get you to recognize their position on the periodic table and relate that information with how many valence electrons. Now we know how many total electrons they have by knowing its atomic number. But now you know how many valence electrons it has by its position on the periodic table. Now we can only do this for the elements Roman numeral 1A through 8A, okay? Now, if everybody in 8A, all the noble gases except helium, they're in group 8A. That means that there are 8 valence electrons, except for helium, there's 2. 8 valence electrons. And here is the whole thing about this. 8 is the magical number that everybody is trying to obtain. You recognize that fluorine has 7 valence electrons, okay? We all agree on that. Now we know there's 7 valence electrons. Yes, fluorine has 9 total, but of those 9, 7 of them are in the outermost shell. The other thing, if you recall, I said that all nonmetals want to gain electrons, okay? Fluorine is a nonmetal. It will gain electrons. And specifically, it will gain 1 electron. It has the tendency to gain 1. Why? By gaining 1 electron, it goes from 7 valence electrons to, guess what? 8. And now it's at a lot more stable state. And by gaining that 1 electron, guess what? Its charge now is a -1. And that is the ion that it's created by gaining 1 electron. On the other end of the spectrum, lithium, we all agree now that has 1 valence electron. Well, think about it from an energy perspective. You think it's a lot easier to gain 7 electrons to give it that magical 8 or to lose 1? What does your intuition tell you? Is it easier to gain 7 or lose 1? Exactly, lose 1. And by losing 1, the next shell now is full. And now it's in a more stable state. So lithium will lose 1 electron. And by losing 1 electron, guess what? It's a metal. And when I stated before, all metals want to lose electrons. And when you lose negativity, you become more positive, right? So lithium would be a positive 1 ion. In fact, everybody in group 1 wants to lose that 1 electron. Doesn't want to hang out with that 1 electron. It's a lot of energy involved to keep it there. And so they're going to lose that 1 electron. So everybody in group 1 will have a positive 1 charge when they lose that electron. Okay. Sodium, which you put on your french fries, has a +1 charge. Okay. The sodium ion is what you put on your french fries, not the element. You put the element on your french fries, you will cause a little explosion because it will react with the moisture, generate hydrogen, and go boom. So, but the sodium that you put on your french fries is a sodium element that has lost 1 electron. And why did it lose 1 electron? Because now the next energy level in is full. The outermost shell of that sodium element has 1 electron. It takes up too much energy to maintain it, so it gave it up. It becomes more stable. Okay, that's group 1. What does it tell you about the metals in group 2? What will be their final charge? What can you extrapolate from there? What will be the ionic charge of magnesium and calcium, strontium, and barium? What will be their charge? How many valence electrons? Exactly. Sam, you got everybody in group 2 will end up with a +2 charge, okay? Because they're going to rather lose 2 electrons, which is a lot more energetically favored, than trying to pick up 6 to get that 8, okay? And that's why the metals want to lose electrons, because now they become the next energy. By losing the outermost shell, they get rid of it and become a lot more stable. Whereas in the other end of the periodic table, the nonmetals, they're closer to the noble gases, and they're more have the tendency to gain electrons, because by gaining electrons, now they have that happy magical 8 number. Okay. All right, that's good. So we were at lithium here, the 2s2. So after lithium, we got beryllium. And if this were beryllium, then this 1 becomes a 2. Okay, and so I could put an arrow here. Now, as we shoot across the periodic table to boron, check it out. Boron has 5 total electrons, okay? 5 total. Check your periodic table to verify. We're talking about boron, element number 5. Notice its position on the periodic table. It's under group 3A. 3A tells me there are 3 valence electrons. Okay. And guess where they're at? 2 of them are in the s orbit, 1 of them is in the p orbit, and they're both, all 3 of them are in the second energy level. Okay. And boron is a, is a metal that will lose 3 electrons. Okay. Lose these 3 outermost electrons, because once I got rid of those 3, I end up with a +3 charge, but my next energy level is 4, okay, which would be 2 electrons. Okay. Now we go across, that's boron. Now we go across to carbon. Okay, oh, let me back up for a second, because with boron, that's where we introduce the P orbits, okay? Notice I said in group 3A, think of those from 3A to 8A, think of those as the P elements. So the very first electron goes into the P orbit, okay? As we go across the periodic table, we keep adding. So the next one will be carbon. Okay, so I don't put that one electron in the same box. I want to keep, I fill up each orbit first, then I go back and start filling up where I can add. So that's carbon. Okay, carbon is in group 4A. Now here's your reference point. Everybody in group 4A, they're in the halfway mark, either direction. They're on the fence. Okay, look at it this way. They're on top of the fence. I can fall one way or I can fall the other way. Depends on my conditions, right? Yeah, which means the following. Everybody in group 4 can either gain 4 electrons or it can lose those 4 it's got. Okay, it's on the fence. Now, prior to the group 4, everybody in 3 back, they lose electrons. Okay, because they're not on top of the hill yet. All right. So on the hill, on top of the fence, I should say, you can lose 4 or gain 4. So what does that tell you? That from 5 forward, everybody gains electrons. Okay. So the next one up after carbon, guess what? Here comes nitrogen. Nitrogen has 7 electrons, doesn't it? Total. 7 electrons. Of those 7, 5 of them are the valence, the outermost shell. Okay? And what do you think nitrogen, this is nitrogen, this represents nitrogen. So right now it's 2s2, so we got 2p3 to represent those 3 electrons. So the electron configuration for nitrogen would be 1s2, which is the first set of electrons, then 2 electrons go into the 2s2, and then we got 2p3. So that would be electron configuration for nitrogen. Now, nitrogen is a nonmetal. We all agree, remember I told you, put it in your long-term memory, nonmetals gain electrons. How many electrons do you guys think nitrogen will want to gain? What we got here? 3, exactly. And furthermore, by gaining 3 electrons, what kind of charge would it have now? Negative what? It gained 3, -3, exactly. That's correct. So now nitrogen, the element nitrogen has a 0 charge. But because it is in group, the group it's in, it's a nonmetal, it's going to gain electrons, specifically gain 3. Because think about it. From an energy perspective, we had carbon where it's got 4 valence electrons. So from an energy perspective, losing 4 electrons or gaining 4 electrons would take roughly the same amount of energy. But now I got 5 valence electrons. Is it easier to gain 3 or to lose 5? Well, definitely easier from an energy perspective and more stable to gain 3, because by gaining 3, now the outermost shell is full with that magical 8 number. Okay, so that's nitrogen. And guess what? Let's move it on up to the next one. Okay, which is oxygen. Now I can start filling up the rest, because nitrogen, all the P's are full, so now I can add it to any of the boxes is empty. Oxygen has 8 electrons, right? And of those 8 electrons, 6 of them are in the valence shell, okay? Which means what? It's a nonmetal. How many electrons do you think oxygen, this is oxygen. So the electron configuration for oxygen would be 1s2, 2s2, 2p4, okay? Here's the outermost shell, the p energy level. How many electrons do you think oxygen will pick up? Because it's a non-metal. Keep in mind, 2, exactly. Therefore, its charge would be, or it'll be correct. Its new charge would be a -2 because it picked up 2. See, it's got room for 2 electrons. Once it picked up 2 electrons, guess what? Unstable now, a lot more stable than hanging out there with, you know, having these 7 of them, 6 of them in the outermost shell. Okay, so let's now take it to the next one, and I'm going to bring it all the way through. The next one would be fluorine. See, I haven't erased a lot of the stuff. All I did is just erase some of the things. Fluorine, okay, just has a total of, you know, 9 electrons. It is in group 7, okay? Group 7, this would be fluorine. So this would be 5. So it's got 7 valence electrons. Again, what do you anticipate fluorine to have? How many electrons would it gain? It'll gain 1, resulting in what kind of a charge? A -1, exactly, okay? By picking up an electron, and now it's more stable, because why is it more stable? Because let's take it all the way through and then we'll go on. The next element, let me erase this. Is neon, okay? Neon has 10 electrons. Okay? How many valence electrons does neon have? 8, stable number. The same number of valence electrons that the noble gas below it would have, argon and krypton. All of them have 8 valence electrons. They have different number total, but all of them have 8, because that's the number they're striving for to get to be stable. Once they have 8, all the orbits are full. Notice here, the valence electrons, they're full. If I pick up an electron, I can't put it anywhere. If I pick up another electron, which would be potassium, it needs to go to the next energy level. This would be potassium right there. I need to go to energy level 3. Okay, so I hope that you can recognize here before I go to potassium, that prior to that, when I was doing nitrogen, oxygen, fluorine, by picking up electrons, now what the nitrogen, oxygen, and fluorine now have, by picking up their respective number of electrons, 3, 2, and 1, they have the same number of electrons as neon. Neon is a noble gas. This is neon. So neon, there'd be electron configuration. 1s2, 2s2, 2p6. Everything's full, 8, stable noble gas. Okay, and then the trend continues again. I start with the next one. I start with potassium. I go across the periodic table. Okay, but we add a little bit different here because the D's come into play. Okay, now, well, I won't introduce this just yet. All right, so like I said, I wish I could flip that over if you can. Take this graph and flip it over and start off energy level down and basically have an upside down pyramid. Okay, that's what it should be. All right, so let me just briefly talk about these. Well, I'm going to talk about the S and the P. The D orbits are some crazy looking orbits that are beyond the scope of Kelvin 30. But you're more than welcome to get online and search what a D orbit looks like, and they kind of look like Star Wars items out in space. They're pretty crazy looking. But these orbits that you see here are nothing more than mathematical equations that have had data plotted to the mathematical equation to give you this three-dimensional picture. So the S orbits are round in shape, spherical, okay? And so that image that you see represents the probability of an electron being anywhere where you see that color. Obviously, the darker the color, the more probability of the electron being in that area, okay? Now, and there's only one orbit. And keep in mind, the only difference between a 1s, 2s, 3s, 4s is just the size, okay? So what does that tell you? Think about this. First period number 1s. And what is the difference between a 1s orbit and a 7s orbit? Obviously, the size. What does that tell you about the relative radius of a 1s element compared to a 7s element? It's bigger. So the trend going from the top of the periodic table to the bottom, the trend of diameter radius is that the elements get bigger, obviously, as they get bigger, okay? Because the energy levels, you get more energy levels. Okay, so the S orbitals are round in shape. Now, with respect to the P's, they call these the dumbbell shape. Okay, there's 3 P's, both in the X, Y, and Z axis. Again, these represent mathematical equations in the 3 dimensions, and those colored areas represent where the probability of an electron being. Okay, so those are the 3 orbits, and I used to have links for the D's, but they no longer function. But you can, if you want, just Google images of D and F orbitals, and you'll take a look at them, and there's some crazy looking ones, but we're not gonna study those other than to say there's 5 Ds and 7 D orbits. Okay, all right, so we got 1s orbit, 3 Ps, 5 Ds, and 7 Fs. And each one can handle a maximum of 2 electrons. That should tell you how many electrons you can put in maximum at each energy level. Okay, we'll go through some of those. Now, this is the equation I was telling you about using the order of assigning electrons. You start off with the 1s, you move to the 2s, the 2p, and then the 3s, and then the 3p, then 4s, and then at the 4s, then the 3d come into play. Now, here's the thing that can be confusing. Oh, I didn't realize the time. Tell you what, let's take a quick short break. Let's come back at 15 till. Okay, it's I got 2:29, so let's come back at 15 till, and we'll continue here. Okay. All right. Let me pause. Okay, welcome back. I just saw a message here, Natasha, saying if I don't do 2 attempts on homework in Canvas, it won't give me the correct answer. That is a problem with Canvas. For example, all right, you have 2 attempts, you do your first attempt, and maybe you get 10 out of 10 of the homework, and you're happy with it. And you're correct. It won't show the homework, the incorrect answers. But if you got 10 out of 10, you got the answers are correct. But let's say you got 9 out of 10. It won't show you what the correct answer is unless you do the second attempt. Now, it's set up to do that so that if you do a second attempt and you look at the ones you missed the first time, that you can go and research it, because the second time you may or may not get the same question, because they do rotate. You will get something that's similar. I don't know a way around that if you're happy with the first grade and you don't want to do the second attempt. The only way around it, it's a good question, is that run through the second attempt and just throw anything that you want, because Canvas will keep the best score. Okay, and so if you're happy with the first grade and you want to know if you missed one and you want to know what the answer was, obviously you can look it up, obviously, or do the second one, just throw in any answer. And if you got a 5 the second time, it would keep the 9 of the first time. That's the only way around it that I'm aware I can do. Okay, because even if the idea is if you miss, half of them the first time, the idea is you have to go back and look at the ones you missed, look up the answers, and then attempt the second one without being given the answers, if that makes sense. Okay.
I have a question.
Sure, go ahead, Trevor.
Do you know why we have to label it as 1s, 2s, 2p, or whatever? Like, let's say it was like 2p5. Why couldn't we just put 2p5? Why do we also have to put the ones before it? Because you could just infer that they're not. They have to be there.
Good question. 2 reasons. One, there is a shorthand way to write the electron configuration by putting the noble gas beforehand in brackets. And now it's going to demonstrate that, and then put the rest of it. The whole idea here is to understand how the electrons are put in their different separate order, all the way starting from 1s orbit. But you're correct. That's correct in that statement, is that the assumption is that you understand that everything's there for, let's say you do potassium, everything's there beforehand. But it's not. If you didn't know that, you might say, okay, it's 4s1, and think that's it. Well, if you didn't know there's more to it beforehand, that would be incorrect. Do you follow what I'm trying to say?
Yeah, that makes sense. Thank you.
Yeah, but there is a shorthand way, and the way I'll discuss that, instead of having to write it all out, beginning this is just asking you to write it all out to make sure that you understand where all the electrons go. Okay, but once, obviously you do a few of them, we have a shorthand way that, let's say you're doing potassium, for example, you look for the noble gas that's behind it, and you put that in brackets, its symbol, and then you just proceed from that point forward. Okay, so, and I'll have some examples on that. But Natasha, did you get what I mentioned about the homework issue?
Yeah, I did. I just assumed that after, the due date of that particular or any of the homework assignments, that it would automatically then give you the answers because you reach the due date of that assignment.
Well, let me, that's a good point. Let me make a note of that, and you should be able to show that.
It doesn't on any of them. And, I like on chapter 4, I missed like half a point, and I'm so curious as to what I did wrong. Okay. And I don't know. All
right. Let me find out. I'm going to talk to tech support about that. How after the due date, I can show the answers regardless of how many attempts you did.
Yeah, that's what I was thinking it would do automatically. That's why I didn't go in there to attempt a second.
Okay. But for right now, just if you want to, in that half point, you want to know what it was, just run the second one, just throw any answer, because they won't keep the low answer, it'll keep the highest answer, the score, I should say.
So even after, let's say, the due date of chapter 4's homework, which was yesterday, right, I can still go in there and do a second attempt. And
yeah, but it would treat it as late. But since you're happy with the first score, you can throw in any answer, and then it'll show you the answers afterwards until I can fix that, if it's fixable from my end.
Okay. So it
Okay.
won't affect my top score then.
No, if it does, let me know, but Canvas is set up to keep your highest score.
Okay.
Regardless, whichever of the two attempts, you should keep the highest score,
All right.
even if one of them is late. Now, what's happened in the past, is a point, is people do not, maybe at the end of the semester, for whatever reason, maybe the first attempt, they got an 8, and they want to go back and redo the second attempt, and like weeks later, it will treat that, and they get a better score, but it will treat it as late and only give you half the credit. If that were to happen, just let me know, and I will make sure that that lateness penalty is removed.
I just tried it.
Yeah,
Yeah, and after you're done with it, it saves the attempts, like attempt 1, and you click on the link and it brings you to the first one you tried.
uh-huh.
Yeah, so it saves it on the top.
But
It'll,
it saves your
you.
best score.
It saves all the attempts. So
All
you
it-
can just go
yeah.
back. Yeah.
All the attempts are saved, but I want to make sure that it does keep your best score
Yeah.
after the
Yeah.
due date. Did it do that?
It doesn't show you the answer for the first one.
Oh, it doesn't?
No.
Okay, well, let me find out. You can get the answer shown after. Let me talk to tech support and ask him how I can set it up so after the due date, the correct answers are shown. That would be the easiest fix to all this.
Yeah, definitely.
Yeah, okay. So I have it I have it on my notes to know. Once I find out how to do it, if it's doable, I'll get it done. Okay,
Yeah. I was going to ask you about this question anyway, so I'll send
Sure.
you it in Canvas.
okay.
Alrighty.
All right. All right, good questions. Eduardo says it does keep the best score. That's good to know. Otherwise, Canvas has a trouble, has a problem there. Oh, what I was going to say about the second attempt. Let me clarify that. Let's say you do the first attempt and you did it before the due date, which is within the due date, no problems there. And you score, let's say, for example, it's homework, obviously, and you did an 8. Well, maybe down the end of the semester, you want to go back and do your second attempt, okay? And you do your second attempt, and this time maybe you get the full 10. But because Canvas sees it, your second attempt is after the due date, it will penalize you, okay? So if you do the second attempt, and there's a key thing, and you did the first attempt within the time limit, and your second attempt is better in score, you want to keep that, then let me know, and I would take the lateness to give you the better score. If you did the first attempt at the correct time due date, okay? That makes sense? Obviously, if you did the first attempt after the due date, and then you did, that wouldn't be true. I couldn't do that. But only if you do the second attempt at the due date or before the due date, and you did, and it, I just confused you all again. Let me try this again, okay? Let's say you do homework, you only did one attempt, and you want to do the second attempt after the due date to improve your score. That's perfectly acceptable. If you did the first attempt when it was due and before the due date, and your second attempt was after the due date, but it's counted as late, and it's a better score than the first attempt, which was done on time, I will fix it so you can get the better score if you did the first one on time. Is that better? Okay. Clear as mud, right? All right, no problem. All right. Okay, so let's go back to this, and like I was stating about this whole thing, The purpose of this whole electron configuration is to give you an idea, specifically mostly on the outermost shell, on how the electrons are filled up in the outermost shell. Because again, all the action, all the chemical processes are occurring on the outermost shell of the electrons. Okay, that's where all the action's at. And it also gives you an explanation as to why nonmetals want to gain electrons. You know, I could simply say to you, okay, nonmetals all gain electrons, and you know, memorizing, that's the end of the story. Well, it really doesn't explain why. You know, I like to have an explanation just to be told that's the way it is. No, what you can see hopefully now is that with nonmetals, because they have room to gain electrons, and that way they fulfill that magical 8 number, that they have the tendency to want to gain electrons, be it 3, 2, and 1, depending where they're at in the periodic table, resulting in a full outermost shell, but they have a charge now, specifically a negative charge, okay, because they gain electrons, which are negative charge. On the other end of the spectrum, in the metal side, they have in numbers of electrons in their Vega shell that are way low below the magical 8, okay? So it's easier from an energy perspective for these metals to lose 1 or 2 electrons or even 3 electrons than it is to gain, you know, 5 or 7 electrons to get that magical 8, okay? So you can see there that the metals, because of those electrons and how many they have in the Vega shell, they're going to have the tendency to lose electrons. Okay. Second point is this, that our model shows that because of the spectrum, the emission lines, that these electrons on these atoms, our model shows that they are in very specific energy levels. You know, before this, it was just thought the electrons are just thrown in there like a hodgepodge thing and just somewhere on the atom. But now, based on the emission spectrum and in our model, we know that they are at very specific energy levels, okay? All right. And we have 7 energy levels. And within the 7 energy levels, let me back it up for a second. Within the energy levels, there are sub-energy levels, which are called orbits. There are 4 types. The first energy level only has the s orbit. The second energy level has both the s and the p orbits. And the third energy level has the sp and d orbits. And then the fourth has the sp, d, and f. Now, with that information, knowing that each orbit can handle a maximum of 2 electrons, can anybody tell me the maximum number of electrons that you can fill in the third energy level? What is the maximum number of electrons can you put in the third energy level, given the information there? What do we have? 14? Does that seem about right? Okay, let's look at the third energy level. Okay, here's the third energy level. We got 18. Okay, well, let's not guess. Let's work it through. The third energy level has the S, the P, and the D. Okay, there's 1 S, there's 3 P orbits, and there are 5 D orbits. Each orbit can handle a maximum of 2 electrons. So I can put 2 here, 2 there, 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 2 there. So how many maximum number of electrons can I have total? I got 10 sitting there, right? 6 sitting there, and 2 sitting there. And your water, you're correct. There's 18. Okay. What about the fourth energy level? What is the maximum number of electrons I can do there? Yeah, 32. Exactly. For the fourth energy level, the max number of electrons that I can put in here would be 32. Okay. Don't confuse this question with how many what is the maximum number of electrons that I can put in the p orbit? Okay, what is the maximum number of electrons can I put in a p orbit? 6, exactly. Okay. And we asked the max is 2, the D's the max is 10, and the F the max is 14. Okay, so sometimes the questions pop up, they're asking specifically for the orbit, or sometimes they're asking specifically for the energy level. So for the energy level number 2, the maximum we can put in would be 8, right? 6 in the P and 2 in the S. And for the first energy level, the max we can put in is 2, just in the S. Okay. All right, so let's go back to how we fill them. And the way we fill them in this order, here's a diagram to help you out. You start with the 1s, you fill that up, and go to 2s, and then 2p, 3s, 3p, 4s, etc. Now the 3D, you notice the 3D kick into it when we reach the third level. But here's the confusing part sometimes, is this. If we look at the 3D orbits would not come into play until we reach these elements in here in the inner area. Let me get my mark. So this one, scandium 21. We would think that, okay, we recognize that these are the D electrons from here that way, okay? These are all the D. And given what we did before, we said there was 1s, 2s, 3s, 4s, etc. We would think, okay, this would be 4D, right? That would be our logical conclusion. And that would be a good conclusion. However, it turns out that the D orbits for number 21 do not come out in the 4th energy level. They are really, because of the mathematics of it, the energy level is really in the 3rd energy level. So it's not a 4D for number 21, it is 3D. And only when you hit number 21 that you have to be concerned with the D electrons, okay? And when you hit 21, then that D electron will be in the 3rd energy level. So what does it tell you about number 39? You would think, okay, it must be 5D, and the answer is no, it's not 5D, it's actually 4D. And so for the D orbits, the energy level that they come out in is 1 less than the period that they're in. So number 39, its D orbit should be in the 4th energy level. What does that tell you about 57? Well, that would be 5D. See how that works? Okay. And so for D electrons, their energy level where the electrons start to come out will be 1 less than the energy level that they're in. Okay. With respect to the F, which is down here, okay, the F orbits, these are the ones we classified as the F, okay, they begin 2 energy levels less than the period they're in. And so here we got 4F, okay, and the next one over would be 5F. Okay. So the D orbits come out 1 energy level less than the period they're in, and the F orbitals begin 2 energy levels less than the period that they're in. Okay. And that is why the 3s, the very first D orbits come into play. You would think they're from the 3rd period. No, There's no d orbits in the third period. That comes from the elements that begin in the fourth energy level. There's a question. Okay, again, it has to do with the energy level and the mathematics involved is this whole thing. That when they solve for these orbits and they solve the mathematics, they come up with these crazy equations. They find that their energy level, the value for their energy level is not at the period that they're in. That in fact they're a lot less, they're a lot more stable, one energy level or two energy levels from where they would expect them to be. Okay, purely all mathematics. And now the kicker of all this, which when I first was introduced to this information, this is a whole area called quantum mechanics, which was a big head scratcher for me. Because, okay, I like mathematics, but some of this mathematics is pretty high level. And it's one of those classes where, you know, you got to take if you want a degree in chemistry. So it turns out that all these equations that are come up, and these are three-dimensional equations, and they're pretty rough looking. They're all derived from the hydrogen atom. Okay, here's what's happened. They looked at the hydrogen atom. They came up with an equation, and it fit very well. They solved for it. They found an equation to fit the hydrogen atom. When they moved up to helium, something happened. Well, you added an electron. And so now you added an interaction between two electrons, which added another part of this mathematical equation, which made it more complicated. So what was done is they said, well, the electrons are interacting with each other very little. Why? Because they're negative charge and they're not going to see each other very well. So, you know, we can, part of the equation, we can truncate and eliminate. And that's what they did. So there was a lot of interaction. Then you add a third electron and so on and so forth. It got more complicated, but they did a lot of assumptions and so simplified their mathematical equations. And they ended up with the model that we have now. Now, does that fit what we know so far? It does. Does it fit 100%? No. But that's the best we got at this point, which is a lot better than where we were a while back when we had the plum pudding model. Okay, at least now we know a little bit more. You know, the question is, are we barking up the right tree? You ever heard that expression? That I don't know, yeah, to be quite honest. But that's the best answer I can give you, Eduardo. It has to do with the mathematics involved with these equations. And if mathematics is your game for anybody, and you want to get into high level stuff, quantum mechanics might be your cup of tea. There's a lot of new stuff going on in quantum mechanics. All right. One thing, a side note, quantum tunneling. Imagine going from point A to point B without going through anything. Magically go, you're here, and next moment you're here. Okay, called quantum tunneling. That's a fascinating concept. All right, well, that's beyond the scope of Chem 130. I can get off from the side note. I don't want to do that. It's a good question, Eduardo. Like I said, it's the best answer I can give you. Any other questions? All right. Okay, so this is the syntax, if you will, to do your electron configuration. I explained to you, notice where the 3D comes into play. You know, keep it in mind that for the d orbits, those electrons are one energy level less than the period that they're in. And for the F electrons, there are two energy levels less than the period that they're in. Okay. All right. Now, be able to do at least the electron configuration for the first 20. Now, you're more than welcome to sit there and memorize memorize them. That's totally up to you. Or I can show you in a turn-to way using the periodic table. Okay, and just recognizing where they're at. And let me pull up a different periodic table because the one I have is pretty marked up with the other information. And give me 1 second. Okay, where is, okay. All right, so let me pull this one up. And this one here is not as, this is the one that you may have, and it's not marked up. Okay, well, let's do some electron configuration of, I don't know, the first 20. We can do it very quickly. Okay. Now what I'm going to do is I'm going to go ahead and mark the period. 1, 2, 3, 4, 5, 6, and 7. Then also keep in mind that I'm going to call these the S as in Sam, call these the P and the P. Now we're going to do the first 20, then I don't have to worry about these guys in here. These were called the D's, okay? So we're going to do the first 20. All right. Hydrogen, very first one, okay? First thing I know, let me erase this here. Right here, I use this white area here to write on. Doing hydrogen, okay? First thing I notice is it is in energy level number 1, so I can put 1. Okay, it is in the first column, okay, which is the S element, so I can put S. And it's in the first column, so I can put superscript 1. I'm done, okay? That is the electron configuration for hydrogen. Okay. Now, I go across to helium. Very straightforward. I get rid of that 1, I add a 2, and I'm done. That is helium. Okay. All right, let's go to lithium. Lithium, first thing I notice here is this. Let me erase, I start from scratch here. Okay, we're going to do lithium. All right, so notice it's an energy level number 2. So I know that the 1s1 will be full. It's already filled up, excuse me, the 1s2. Those 2 electrons are full. And then it's in the second energy level, so I can put a 2 there. And it's in the first column like I did with hydrogen. I can put an S, and being in the first column, I just simply put a 1, superscript 1, right? Now, the superscript represents the number of electrons. 2 plus 1, isn't that 3, right? I got 3 electrons for lithium. Lithium has 3 electrons, is element number 3, okay? Of those 3 electrons, 1 of them is in the outermost shell in the second energy level, which is why it's in group 1A. It's got 1 valence electron, okay? And the other 2 are in the next shell in, okay? 2 bits of information. I got 1 valence electron. It's a metal. When it loses that electron, it's going to be a positive 1 charge. Okay, move over to the next one. Beryllium. This guy here has got 4 electrons. Okay, I'm just moving across. I'm still in the second energy level. I've added an electron, so I can remove that 1, and now I put a 2. Okay, now beryllium has 4 total electrons, right? That's the atomic number. Of those 4, do I not have 4 electrons here shown by the superscripts? 2 in the S, 1s, 2 in the 2s, total 4. It has 2 valence electrons that exist in the outermost shell, which is the second energy level, okay? Now, I move over to boron. Now I enter the domain of the P elements. I'm still in the second energy level, okay? Now I can't put any more in the S because why? The maximum for each orbit is 2 electrons, so I have to go to the next orbital. Now from the energy perspective, the S orbital is lower a little bit than the P, so I fill the S first, then I fill up the P. Okay, so it's 2P, I'm still in the second energy level. I'm in the first column of the P element, so I can very simply put a superscript P. Now, does not boron have 5 electrons total? Yep, count my superscripts. Here, let me fix this up a little bit. 2 plus 2 plus 1, doesn't that equal 5? Yep. 5 electrons. How many valence electrons does boron have? It has 3. It's in group 3. Of those 3 valence electrons, one of them is in the p orbit and the other 2 is in the s orbit. See how that works? Now let's do carbon. Carbon's the next guy. No big deal. I take that and that becomes the second column of the p. So I got P1, P2, so this becomes P2. Doesn't carbon have 6 electrons? Yep. Okay, look at my superscripts, 2, 4, and 6. I got 6 electrons. It's in group 4A, Roman numeral 4A. Okay, that means I got 4 valence electrons. 2 of them are in the p orbit, 2 of them are in the s orbit. Okay. All right, now we can continue with this exercise and go all the way across the neon. So nitrogen would be P3, okay? That'd be nitrogen. Oxygen would be P4, okay? Fluoride would be P5, okay? And then finally with neon, guess what? P6. That would be neon. Okay, and I can put neon and put it in brackets, neon. Okay. Now when I go to number 11, which is sodium, sodium is in the 3rd energy level. Okay. So I can do this. I can do it longhand, unless the question says don't do it longhand. If I continue with shorthand, I got 3rd energy level. I put a 3 there. It's in the first column of the S elements, so that's 3s, and it's in the first column, so it's 3s1. Okay. Again, does not sodium have 11 electrons? Sure enough. Count my superscripts. I got 11 in my superscript. How many valence electrons does sodium have? It has 1. It occupies the 3rd energy level, okay, which is consistent with where it's at in the periodic table. Okay, then to go to the next guy, which is magnesium, I'd simply get that S1 and put a 2 there. Okay, and when I go to aluminum, guess what? I introduce the 3P, 3P1 for aluminum. And then I go all the way across to argon. I go 1s2, 2s2, 2p6, 3s2, 3p6. And there I am for argon right here. Of course, I bypass silicon, phosphorus, sulfur, and chloride, but the same scenario we just did for the one above that. Okay, which brings us to number 19. And what do you think that's going to happen there? I got to go to the next energy level, which I'm running out of room. I'm going to go over here. 4s1, that is potassium. Calcium, guess what? Take that 1, convert that to 2, 4s2. So for calcium, which is number 20, 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, shoot over to 4s2. And that is calcium. okay? And all I did was find its position on the periodic table, remembering my S elements, remembering my P elements, okay? And then remembering the energy level that they're in, okay? Now, if by chance I'm asked to do number 21, okay? Now, from here to here, these are the D elements. And what I do, remembering that when a D start, and I only start when I start with number 21 here, that I gotta be one energy level below its period. So this will be 3D1, first column, okay? And for Chem 130, if we happen to go through the D elements, it'll be sequentially D1, D2, D3 to D10. We'll find, I have a table here that shows you that in reality, there's exceptions to the rules and we're not gonna go into them, but just simply keep it sequentially D1 to D10. The same is true for the F, if we happen to go into the F. You never know, those could be extra credit questions, you know, things like that can pop up, but definitely for sure, be familiar with at least the first 20 and how to do its electron configuration. And I just demonstrated that by just finding it on the periodic table. Or alternatively, you can utilize this table to help you through, okay? I prefer the periodic table. You can go very quickly because as you go through each one using the periodic table, you start to pick up a trend, realize why certain things gain electrons and why some lose electrons. So let me go and do the shorthand. So after 3D, we go back again, and Eduardo had the question, yes, that is correct. Let me go back to the periodic table. That if after you are done, like, let me highlight this. Let's say right here, from here, let's say I was doing this. Okay, now let me introduce a shorthand way. Let's say, for example, I need to do number 21. And they say it's okay to do the shorthand. So I find its position, then I go back to the previous noble gas, which in this case is argon. So I can write argon, and then I put a bracket around it, okay? 1, 2, 3, and 4. And then I'm gonna continue from argon forward. So it'd be 4s2, and then scandium is 3D, so it'll be 3D1. Now, some people put the 3D1 first, then the 4s2. It makes no difference. It won't. Okay, in my opinion, the fact that you're there is good. Now, if I went across to zinc to right here, okay, that was showed zinc. I can go all the way across to 10. That would be zinc. Okay. Now, if I need to jump back to number 31, then I go back to the 4P because these P's stay in that period. So if I was going to do number 31, then there would be 4P1 for this one. Okay, you go back to the P. And that's to answer Eduardo's question, okay? And the same is true for the F. Once you do that, you go back to whatever period you're in, okay? You only switch for the D and the F. Okay, good question. But like I stated, stick with, if you got the first 20 down pat, you should not have a problem. And if you wanted to do, like I said, the shorthand way, let's say you wanted to do sodium, okay? And it's okay to use the shorthand method. While you find sodium in your product table, look for the previous noble gas before it, which is neon. So you can write Ne in brackets, not parentheses, in bracket. Okay, this is 1, 2, and 3. Realize that sodium's in the third energy level, and it's in the first column. This is the S elements right here. So it'll be S, and it's the first column, so there you go. So the electron configuration for sodium, the shorthand way would be neon in parentheses 3s2. Let me demonstrate both shorthand and longhand. Okay, so we got sodium here. We got 1, 2, and 3. Longhand will be 1s2, go across, and then 2s2, 2p6. So see, we're going across here, here. We went across here. We went across here, and then 3s1. Okay, that's where we're at. That's longhand. Shorthand, we find previous noble. This here is 6. Is the electron configuration for neon. So we can put that neon in brackets and 3s1. Okay, shorthand, long. Okay, you can do that for, unless the question says otherwise, you can do that for any of the elements. So if we were to do potassium, well, potassium, previous noble gas is argon, so it would be argon, bracket, 4s1. That color doesn't come out too good. So it would be argon, bracket, little r, 4s1, and that would be for potassium. Okay. All right, for shorthand. All right, so what? It's 4:27. Let us stop it here. It'll be slide page 5, slide 25. All right, let's stop it here. We'll continue on Thursday. We'll get this knocked out, this chapter done on Thursday too. So